Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On. In this tutorial video, I'll go through this old syllabus. Well, not really that old, it was November 2015 for this 9701. Cambridge International A-Level paper 4-3. I think this is paper 4, variant 3. So back then, from 2015 backwards, there was section A and section B. Section B covers some option topics, most of which are no longer relevant in the context of the new syllabus from 2016 onwards. So you can use older papers for revisions, but always keep in mind the current specifications and curriculum. So have that document for the examination year that you'll be sitting for your exam, so that you are not, necessarily troubled or worried about stuff which are no longer in the syllabus. Okay, so throughout the tutorials, I will try to skip over stuff, or I will explain stuff where they are no longer relevant to the current specifications or the current syllabus for the 2022 version of this Cambridge International syllabus. Okay, most of the contents within, however, are completely relevant for any 14 to 16, sorry, not 14 to 16, but 16 to 18 years old students, obviously. In this first question, the dissolving of an ionic compound in water, so is accompanied by this energy change, and this energy change per the stoichiometric amount is expressed as kilojoule per mole, which is this enthalpy change of solution. So when you dissolve 1 mole of the substance in a large amount of water to give an infinitely dilute solution under standard conditions. So you want to be able to describe in terms of bond breaking and also bond making. So what happens to the solid ionic lattice? It started from a giant ionic lattice structure, which consists of alternating cations and anions, as you know. Giant ionic structure looks pretty much like this in 3 dimensions, and they are solid as the particles are tightly packed, and they are held together tightly packed, and only vibrate about fixed positions as a solid. So in terms of the bond that you need to break, so we need to break, better spell that properly. We break the strong ionic bond between oppositely charged ions. Strong ionic bonds between the oppositely charged ion, which I can specify between the Mg2 plus and the Cl minus. And what bond are we forming? When dissolved in water, you are being surrounded by water, you get hydrated. When dissolved in water, the aqueous ions, well, when dissolved in water, they become aqueous ions. So the Mg2 plus and Cl minus become surrounded by water, and they will form ion dipole bond, forming ion dipole bond. So the ions are charged, and then you can talk about water molecule is polar. So these bond formations between the cations and the water molecules. So you have Mg2 plus like this, and then surrounding it will be water, but they will be attracted more to the delta minus of water molecule. So there's no specific coordination, as they are just forming ion dipole bond and not forming a complex just yet. So this thing is called ion dipole bond. The formation of ion dipole bond, when you talk about hydration, you go from gaseous ion, dissolve in water. So enthalpy of hydration is always exothermic. But we are not doing enthalpy of hydration, we are doing enthalpy of solution. So this is not gaseous, this is just dissolving 1 mole of the substance in water. And we know that not every substance want to dissolve in water. Sometimes you get this to be endothermic, where this thing is going to be not very soluble. And then when sometimes you get it to be exothermic, where it is more feasible for this thing to be soluble if the enthalpy of solution is exothermic. Something the new syllabus obviously is to do with delta G equal to delta H minus T times delta S. We talk about delta G being lesser than 0 for feasible and also spontaneous reaction. Of course, in the older pre-2016 syllabus, you don't see question asking on delta G, because this was not in the syllabus back then, but the new type of questions could combine some sort of questions involving the calculation of delta G as well. So enthalpy of solutions involve this formation of ion dipole bond. It's not just between the cations and water, it's also between the anion and water. You have negative charge, so you'll be attracted to the delta plus of the water molecule. This is also known as ion dipole bond because your anion has a charge. Your water has dipole, but on the opposite end when it's interacting with the Cl minus. So, we have gotten 2 points there. What are we breaking and what we are forming there? Okay. In B part 1, what is meant by enthalpy change of solution? So for that 1 mark, we talked about it already. So it's the enthalpy change when 1 mole of a substance, so it's got nothing to do with gaseous ion because it's not hydration, but it's in kilojoule per mole. So 1 mole of a substance dissolve in a large amount of water. Dissolve in a large amount of water to give infinitely dilute solution or to form infinitely dilute solution. There are different variations of this particular definition actually, but what is very important is to indicate that it is 1 mole of something, and this is in kilojoule per mole, and that is why enthalpy change is not really just energy, it's enthalpy change because there's the stoichiometric amount associated with it. That's why it's important to have this 1 mole of a substance and what happened to it, whether it's formation, combustion, atomization, solution, hydration, is to do with 1 mole of something and what is happening to it. Okay. This next question, we are supposed to find the enthalpy change of hydration of this chloride ion. We first started out with this enthalpy of solution. We were given that particular equation on top just now. When that react with a large amount of water, you're gonna get this infinitely dilute solution. Balancing the equation, you get 2 chloride ion as such. That is your enthalpy of solution there. We have to try and relate that to lattice enthalpy. So lattice enthalpy or lattice energy is defined as the enthalpy change when you form 1 mole. When you form 1 mole of the ionic solid from its gaseous ions. Okay, so this must be the lattice enthalpy. And we'll consider the value in a little bit. And then this thing, the gaseous cation going to aqueous cation, that is the hydration of your Mg2 plus. You are just hydrating 1 mole of these gaseous ions, so it's 1 times the hydration of that. However, the next one, the hydration of the Cl minus is a bit tricky because when you think about the enthalpy of hydration is for 1 mole of the Cl minus gaseous ion going to 1 mole of the aqueous Cl minus ion. You go from 2 mole of this gaseous ion going to 2 mole of these aqueous ions. You have to multiply this by 2. So I better write this in a different color so that it is very clear that you need to multiply this by 2 because of the definitions for 1 mole of Cl minus ions. So you multiply by 2 because you have 2 mole of gaseous ion going to 2 mole of the aqueous ion. Now Hess law says that, in AS, Hess law says that the enthalpy change of a reaction does not depend on which path you take. So I'm going to take the indirect route, indirect path. So this is the indirect path going via the lattice energy and also the hydration enthalpy. This is a direct path, so going that way, enthalpy of solution is equal to going against the lattice. So this is minus the lattice because the lattice that we define is for the formation of the ionic solid. It's going this way. If we're going opposite, so it's minus the lattice. Its direction really matter. And then I will add the hydration of the Mg2 plus, and I have 2 times the hydration of the Cl minus. So what do I do with all this information? Well, now that I have gotten the relationship, all I have to do is put in some values. Enthalpy of solution from the question, minus 155, minus the lattice, so it's minus, and then use bracket so that you're not confused between this minus and the minus from the lattice energy as given there. And then plus the hydration of Mg2 plus, so it's minus 1925. Again, use bracket. Very, very important, the use of bracket, sort of primary school mathematics as well as lower secondary mathematics. So what am I going to do now is 2 times the hydration of Cl minus. I'm going to move the other stuff to the other side. So this is minus minus, it become a plus. When I move it to the other side, it become minus 2524. This is a plus multiplied by minus is a minus. When I move it to the other side, it become plus 1925. I expect my hydration enthalpy to be negative because I am forming ion dipole bond from something that has no interaction between the gaseous particles at all, and then I'm surrounding it with water and just forming that ion dipole bond without breaking anything. The formation of ion dipole bond is exothermic. So if my answer is not negative, I know something is wrong. Okay, that's the first thing you can think about. The other thing is, this is 2 times that based on the definition, based on the equations. So do not forget that you need to divide that by 2. So just adding all of this up, minus 155, minus 2524, plus 1925, I get minus 754. Writing down working very clearly is very important, and working systematically is part of the skill as a chemist and also in exam. So what you have is a sign, a value, and a unit, and that is what you do for hydration. Well, not just hydration, for calculation of any enthalpy change per se. The next question is about enthalpy change of hydration of Na plus is minus 410 kJ per mole. And they are saying that this hydration enthalpy of Na plus is less exothermic. So you are forming ion dipole bond, so therefore you are forming weaker ion dipole bond. The question is, why is the ion dipole bond weaker? It is between the cation and the water. You are not changing the water, you are changing the cation. So what about Na plus and Mg2 plus is different? Well, we're going to talk about the charges as well as the sizes. That's why there are 2 marks there. So we can say that Na plus has smaller charge, which is +1 overall, compared to Mg2 plus, +2 charge. What else can we say? We know in AS chemistry that the sizes, we know about sizes. So atomic radii will decrease from sodium to chlorine like that. And these are all straight from AS chemistry. The Na plus going to Al3 plus decreases in size like that. So we know that the Mg2 plus is actually smaller in size than Na plus. And then obviously the anion there, P3 minus and Cl minus, just to complete the story, straight from AS, atomic and ionic radii. So what do we know there? We know that Mg2 plus, well actually maybe I should start off with Na plus. It doesn't matter as long as you get the correct trend. So Na plus is bigger in size than Mg2 plus. So overall, what we can say is about the charge density. So charge density is part of that idea in the group 2 chemistry when you talk about thermal stability as well as solubility kind of assay. So the charge density of Na plus is smaller than that. That refers to the charge density of Mg2 plus. Therefore, Na plus forms weaker ion dipole bond with water molecule compared to Mg2 plus there. Now this last question is a 4 marks solubility assay. So you will no longer be given this Roman numeral. Instead, the new type of question will give you as group 2 sulfate like this. So first of all, what is the trend? Describe and explain. We know that group 2 sulfates become less soluble down group 2. So the way I think about it is I know about barium sulfate. So barium sulfate is something that you would have precipitated out as a test for sulfate in practical. If you have done practical before, there is. So there's barium sulfate, which is a white PPT. Now magnesium sulfate is not like the most soluble thing in the world, but magnesium sulfate is just very slightly soluble in water. Okay, so actually calcium sulfate is used as a hardening agent when they make tofu. If you have eaten tofu before, they make it with a little bit of something called gypsum powder, GYPSUM. That is to do with calcium sulfate. So magnesium sulfate is actually not that bad. It's actually slightly soluble in water compared to these really insoluble stuff in water. So having said that, we know the solubility will decrease down group 2. Well, how do we explain this? Down group 2, your essay actually begins like this, yeah? Down group 2, there are more field electron shells. So I've done this essay a lot of times, and you can follow these actually from my other topical playlists as well. If you don't watch this particular video, you need to prepare for it in case it will definitely come out, whether it's solubility of sulfate or solubility of group 2 hydroxide. So down group 2, there are more filled electron shells, so size of cation will increase. Size of cation M2 plus, because all the group 2 ions when they form sulfate will be M2 plus, increases because there are more shells, so it gets bigger in size, but the charge remains the same, but charge remains plus 2. If that is true, what we can say about the charge density is that the charge density of the cation would decrease. The charge density of M2 plus decreases, and if that does decrease, we can expect the lattice enthalpy, the strength of your ionic bond, the ionic solid that you're forming would have weaker ionic bond, so the lattice enthalpy will become less exothermic. But we're talking about solubility, so we also have to think about the hydration as well. If I write out a particular Hess diagram for you, so that's solid plus aqueous dissolved in a large amount of water, you're going to get M2 plus aqueous plus SO4 minus aqueous like this. What happened then is I'm going to relate that with the gaseous ion, because we have to think about lattice enthalpy, just like the earlier bit of this question. So what we get there is what you call the lattice enthalpy, as you form 1 mole of the ionic solid from its gaseous ion. So that going to the aqueous ion, that is the hydration of the M2 plus ion. This gaseous sulfate going to aqueous sulfate, that is the hydration of the sulfate. Not that that is very important, because we don't change the sulfate as we go down group 2. This thing on top there is the enthalpy of solution. So what you could see that this is the lattice enthalpy, and we also have to involve the hydration enthalpy of the cation. The previous questions asked you on the effect of sizes and charges on the hydration enthalpy. And because we have a charge density of cation decreasing, we know that the cations would have smaller charge density. So even the enthalpy of hydration will become less exothermic. The lattice enthalpy will become less exothermic. So both the lattice and also both the lattice and the hydration, I should really clarify this very, very clearly, that both the lattice and also the hydration, but hydration there are 2, they're cation and anion. We are not changing the anion, so it's all the group 2 sulfate. So it's just the cation that are important here, and charge density of cation decreases, so both of them will become less exothermic. Now looking back at the equation which I have written at the bottom, you will see that enthalpy of solution is equal to minus the lattice enthalpy plus the hydration enthalpy of M2 plus the hydration enthalpy of the SO4 minus. Okay, so we are going this way, so going against the lattice is minus the lattice plus the hydration of cation plus the hydration of the anion. Having done that, we can go back to our essay. We know that these group 2 sulfate become less soluble. So that means the enthalpy of solution will become more positive. That means more endothermic. So therefore, the delta H solution becomes, you can say, more endothermic. So that means it becomes more positive. That's why, it becomes less soluble. It becomes harder to dissolve it. Or what you can say is, it can become less exothermic. I think it is slightly easier for us to think of it as in terms of more endothermic. Now, we know that both of them will decrease. They will decrease because the charge density of cation decrease. You want this to become more positive. So this is a negative term. So think about the lattice enthalpy is negative. So when you have minus negative, it's going to be positive, because minus times negative will become positive. And you have positive times negative, positive times negative is going to be negative. So what we get there really overall is we need to consider the balance between the two. In order to get this to be more endothermic, this needs to be more positive. So this needs to be bigger than this going down group 2. If this needs to be bigger than this cannot decrease much more compared to this, which means this has to decrease a lot more compared to this. So we can say that this decrease lesser than this, or we say that hydration decrease more than the lattice. So overall, what we can say is, therefore, the hydration enthalpy of the cation decrease much more than the lattice. That is usually the tricky point there, because it's about the balance. You want the overall to become positive, so this must not decrease a lot. This must decrease more, so that the positive will win over the negative, and they become more endothermic, and they become more less soluble down group 2, because more endothermic, less soluble, more difficult to dissolve it. Of course, when you come to group 2 hydroxide assay, it will be the opposite trend. So this will be the other way around, as you want it to become more exo for the group 2 hydroxide. Okay, that's the end of the 11 mark question. This is a fixed essay for marksting that usually come out as part of group 2 essay that you can prepare for.